Okay, let's jump right in. You know how sometimes the math you're learning in college feels, well, completely abstract, like it just lives in textbooks?
Uh-huh. Totally disconnected from anything real.
Exactly. Well, get ready because today we're diving into a really great example of how those very concepts get used to solve actual problems, big problems even.
Problems that affect pretty much everyone.
Right. We're talking about figuring out the best shapes and sizes for things. Specifically today, food packaging.
Yeah, why is that soup can shaped like that? Or a milk carton? It's not random.
Not at all. There's some serious optimization going on behind the scenes.
And guiding us today, we've got an excerpt from a paper. It's titled Optimal Packaging for Food Security, a Calculus Approach.
Perfect. So
Mm.
our mission really is to unpack how calculus specifically, differentiation and maybe touching on integration is used based on this source to nail down the most efficient dimensions for food packaging.
And crucially, how that connects to something as vital as food security.
Yeah, if you're maybe in the thick of calculus right now, this is such a clear example. It's a direct line from the theory you're learning to, practical engineering.
Absolutely. The source walks through how finding maximums and minimums, which, let's face it, is a huge part of differentiation problems. That's precisely the tool engineers use here.
Okay, so let's take a classic example, one the paper mentions. You need to package a set amount of product, right? Like soup or cereal.
Say 500 cubic centimeters.
You
Yep.
need a container for that volume. But, and this is the key part, you want to make that container using the least possible amount of material.
Makes sense. Less material means it's cheaper, less waste, lighter to ship. It's all about efficiency.
So how does the math work? The source breaks it down,
Mm.
right, for like a standard cylinder.
Right. You've got your basic formulas, volume, V, phi r, and surface area, SAO is 2 par plus 2 har. The trick is the volume is fixed at 500 cc, for example.
Okay.
So you use the volume equation to express one variable, maybe the height, h, in terms of the radius, r, and that constant volume. Ah, right. And then you plug that expression for h back into the surface area equation. So SA depends only on r.
Exactly. Now you've got surface area as a function of just the radius.
Mm-hmm.
And to find the minimum surface area for that fixed volume, well, that's where differentiation comes in.
You take the derivative?
You take the derivative of that surface area function with respect to r, you set that derivative to 0, and you solve for r.
Because setting the derivative to 0 finds the points where the function flattens out the potential minimums or maximums.
Precisely. That's where the rate of change of the surface area is 0. And for the cylinder, the source highlights a really neat result.
Oh, yeah. What's that?
The optimal shape, the one using the absolute minimum material for the volume it holds, happens when the height h is exactly equal to the diameter 2r.
Wow. Okay. So a height to diameter ratio of 1 to 1. That's the mathematical ideal. According to the calculus, yes, that's the most material efficient cylinder. And you actually see cans pretty close to that ratio quite often, though, practical things like stacking or gripping might adjust it slightly.
That's a fantastic, concrete takeaway directly from the source material. It's not just theory. It's deriving actual design rules. But you mentioned integration earlier, too. How does that fit in?
Yeah, good question. So differentiation is really the star here for finding the optimal dimensions, finding those critical points. Integration often comes in, let's say, a supporting role.
Supporting how?
Well, once you have those optimal dimensions from differentiation, you might use integration to, say, precisely calculate the volume of a maybe more complex shape if it wasn't a perfect cylinder, or perhaps calculate total material cost if density varies or something. But the core optimization, finding the best shape itself in this paper's context, that's differentiation.
Got it. So differentiation finds the best spot, the minimum material use, and integration might help calculate related quantities based on that best shape.
You've got it. And let's bring it back to food security, because that's the other crucial part of the source title. This isn't just saving a few cents on cardboard or tin.
Right, there's a bigger picture.
Definitely. Optimized packaging means lower costs all the way through the supply chain, making it, transporting it, storing it. Lower costs can help make food more affordable.
And less waste, too, presumably. Better packaging protects the food.
Exactly. Less damage, less spoilage. That directly reduces food waste. And reducing food waste is a huge win for food security around the world.
So it really drives home that differentiation, maybe some integration, these aren't just abstract exercises. They're tools being used right now to tackle really practical, important challenges like making food packaging better and, in turn, helping food security.
Summing it up, calculus gives us the mathematical language and the methods, like finding maximums and minimums, to figure out the most efficient designs.
Hmm.
It connects complex math directly to, well, tangible benefits for everyone.
It really does. Okay, so here's something to think about as we wrap up. Next time you're in the supermarket or even just grabbing something from your pantry that box, whatever it is.
Take a look at its shape.
Yeah, take a second look. How many other things around you, everyday objects, might have had their designs fine-tuned using the very same calculus differentiation, maybe integration that you might be studying right now?
Mm-hmm.
It's not just math problems, it's kind of the hidden language of how things are efficiently designed all around us.